Today we'll go through chapter 16, which is on scheduling. So scheduling is basically how resources within a company are used to achieve a smooth flow of work, material, and things like that. So we will cover importance of good scheduling, scheduling needs in high volume and intermediate volume systems, scheduling needs in job shops where the volume is very low, and then some of the tools and methods like Gantt charts which are used, priority rules, establishing the time of the use of equipment, facilities, and human activities. These are the basic resources any company has. So that's what is scheduling, how to use it, what should be the timing, when a particular machine will be used, and things like that. So effective scheduling can yield cost savings and increase in productivity, because if everything is smooth, everything flows smoothly, then things will be much better, less cost and better productivity. So the ultimate goal is to achieve a smooth flow, that is without any disruptions. So achieving smooth flow with optimal, I'm not saying minimal, I'm just saying the best or optimal use of resources. So resources are basically your equipments, facilities, and human activities. Now, there could be different approaches to scheduling depending on different situations. Now, let's look at the next slide. So this talks about high volume system. Obviously, approach of scheduling to high volume system or intermediate or low volume systems will vary. We'll start with high volume system. So flow system here is high volume system with standardized equipment and activities, which basically means all the jobs, they will follow the same sequence. More or less, the sequence is freezed. So every part has to go through those specific sequences. A company may decide the sequence and then freeze it. So that all the jobs will follow same sequence. So flow shop scheduling for high volume system. You can see here work center 1. So from there the jobs go to work center 2, and then you get the output. And every job will follow the same 2 steps. So for scheduling manufacturing operations, as mentioned earlier, we have high volume situations, intermediate volume situations, and then low volume. And then also we'll talk about service operations. One example is given. So starting in January, if the schedule is followed, then it can be delivered on time in June. Now let's look at what are the success factors for high volume situations. Process and product design is important. In fact, it is not only true for high volume, but it is also true for intermediate volume and other situations. So how the process is designed, how easy or difficult it is to design the products and manufacture the products as designed. That will contribute to success or failure, depending on how it is done. So if the design is good, if the product design stage itself, the process capability and the production capability has been taken into account, then obviously it will lead to better success. Preventive maintenance is always important. When preventive maintenance is done, obviously it will minimize breakdowns, and that will lead to less and less disruptions of work. So that is another success factor. Rapid repair when breakdown occurs. So even with the best preventive maintenance program, a company cannot avoid breakdown situations. So breakdowns are going to happen, even if it is at a low rate, but then one should be able to respond quickly and repair the system. It should not take forever, because the whole activity will suffer. Optimal product mixes. To arrive at optimal product mixes, there are so many methods companies use, even methods like linear programming, which is totally quantitative method that has been used a lot. Minimization of quality problems, that definitely will contribute to success factors. And then the reliability and timing of supplies. So whatever purchase orders have been placed with the specific lead times, so when they come on time, obviously your productivity will be better. Now, intermediate volume systems. So outputs are between standardized high volume and made to order job shops. Variables of interest generally are run size, or you can say lot size, like how much to produce once the machine is set up, and what should be the sequence of jobs. So all those are very important for even intermediate volume systems. So you must have seen this formula earlier also, I think in the previous chapter. So to arrive at the optimal quantity under these situations, we use this formula. It tries to basically minimize the machine or the process setup cost and inventory cost. Now, when we talk about scheduling low volume systems, so some of the important terms are like loading. So loading is assignment of jobs to process centers. So what specific job will be carried out at which work center? And then what will be their sequence? So within a job, there could be different sequences. So what sequence will be followed? Scheduling for low volume system with many variations in requirements. Generally, the lot sizes will be very, very small in job shop situations. Let's look at some examples to start with. So I look at problem 1. You can also refer to actually example 1 from the book. So that is also similar to problem 1 in the book. So I'm looking at 1, and 3 jobs are given. So jobs are A, B, and C. And there are 3 workers, worker 1, 2, and 3. Now, how these 3 jobs should be assigned to these 3 workers? Suppose the costs are given like this, as given in the problem, depending on the skill level, type of machines, type of job. We start with the step where we do row reduction. So we can have those same 3 jobs, A, B, C, and workers 1, 2, 3. Now, in row reduction, what we do is identify the lowest value in each row. For example, 5 is the lowest value in first row. So we subtract 5 from remaining 3. So 5 minus 5 gives you 0. 8 minus 5 gives you 3. 6 minus 5 gives you 1. Similarly, in the second row, minimum is 6. So if you subtract 6 from each one of them, so 6 minus 6 is 0, 7 minus 6 is 1, and then you have 3. And you do the same thing for the last row. So once you have that, then we do what is called as column reduction. Again, I can write A, B, C, and 1, 2, 3. So same thing we do. We look for the lowest value in each column and subtract. So because the lowest is 0 in the first column, it remains as it is. In the second one, lowest value is 1, so subtract 1. So you get 2, 0, and 1. And then 1, 3, and 0. So once we do that, then see if you can cover all the zeros. Let's say how many lines. So you can cover with 1 line the first 2 zeros, then second line, and then you need basically 3 lines to cover all the zeros. So because 3 is equal to how many rows you have, or how many workers in this case you have, so that means we have found the optimum value. So optimal assignment, job assignment is going to be, so wherever you have 0, for example, worker 3 and machine C. Worker 3 is assigned to machine C. Worker 2 can be assigned to machine B. And worker 1 can be assigned to A. So this we can identify using those zeros. Now in the second question, instead of cost, they give profit. So we don't have to really change the process. We basically need to first convert the profit into cost and then do the same thing. So how to do that? Let me write down. So this is what was given: ABC, 3 jobs, and 1, 2, 3, 3 workers. The data was 586, 679, 453. So what we do is we identify the maximum value and then subtract each number from that maximum value. So we'll subtract each number from 9. You can say this is the revised version. So we have ABC 1, 2, 3. So 9 minus 5 is 4. 9 minus 8 is 1. So we subtract each value from 9, and this is what you get. And then we repeat the same process. So we do row reduction. So you have same pattern here: 1, 2, 3, and ABC. So in the first row, you can see the minimum value is 1. So we do 4 minus 1 as 3, then 0. Same thing we repeat for remaining part. And then we do column reduction. So you have ABC 1, 2, 3. So you can see in the first column, minimum value is 1. So you get 2, 2, 0. And then you have 0, 2, 0, no change, and 2, 0, 2. So now you can see we need 1, 2, and 3 lines to cover all the zeros. And because we have 3 rows, so we found the optimal solution. So optimum allocation is going to be worker 1 goes to machine B. This is the 1. Worker 2 goes to C, because that's where the 0 is. And then third worker can go to A. So this is how workers can be assigned to different machines or jobs. Gantt chart is something very simple to use, and that's what many times people use. So this is used as a visual aid for loading and scheduling. So you can see how the work centers, when they are available, when they are busy. And in fact, in our university also, each classes, assignment of the classes to different rooms, if we make a Gantt chart, it might look something like this. Now coming to loading, in fact, loading are of 2 types. It could be infinite loading, the first one, and it could be finite loading. So in infinite loading, what happens is you do not take into account the capacity. So although capacity is given here, but that's not taken into account. So what happens is sometimes in certain periods, you can see the load is more than the capacity. So there is a overload in 2 different periods, and there are periods with underload. So one problem that could create is when there is an overload, so because the capacity has its own limitations, and if more work is assigned to less capacity, then what will happen is there will be a lot of inventory buildup. There could be a lot of work in progress, so that will obviously increase cost. In finite loading, we have the capacity, and capacity is taken into account. So you can see there's no period when we overload the situation. One example you can think of is face-to-face classes. Generally, university has a cap, for a particular room, how many students can be allowed. So sometimes it is 40. Because of the limited space or capacity, more than 40 students cannot be accommodated. Now loading can also be based on forward scheduling or backward scheduling. So in forward scheduling, scheduling is done ahead from some point in time. If we are talking about today, and then something has to be completed after 2-3 weeks, you start working on it from now, and as and when you are done, the job is done. So basically, you're scheduling ahead from some point in time. Now backward scheduling is opposite. You may have a due date, and then you calculate or work backwards, like if 5 activities are to be completed, then when should you start the first activity? So that is called backward scheduling. So scheduling by working backwards in time from the due dates. Like it could also be, suppose you're planning a holiday for a certain date, and then what activities you need to complete before that. There could be like 10 different tasks to be completed, like booking and things like that. So when that should be completed, once you work out that, that will be called backward scheduling. So schedule chart is a form of Gantt chart that shows the orders or jobs in progress and whether they are on
schedule.
So basically this is used for monitoring the progress of the jobs. Now coming to sequencing. So sequencing, as the name suggests, is basically how jobs are sequenced. What should be done first, then second, and so on. So it is different from assignment. So sequencing determines the order, so that is important here. What should be the order in which jobs at a work center will be processed. So workstation, as you know, is area where one person works, usually with special equipment on a specialized job. So companies generally use what is called as priority rules, which are simple heuristics used to select the order in which jobs will be processed. So there are methods available which allow you to choose the appropriate priority rule. Job time is the time needed for setup and processing of a job. So some of the rules are actually given on the next slide. First come, first serve. Shortest processing time, so do that one first. Or it could be earliest due date, critical ratio, and things like that. So out of this, in fact, the first three are called local rules. So they are local to a workstation. They are about a single, we are talking about a single workstation when we talk about the first three rules. Whereas the next two, you can say, are global, where more than one workstation may be involved. So here you have one workstation, and here you have more than one workstation. And the last one, which is a rush or emergency, so that could be either global or local. It depends on the situation. There are certain assumptions to these rules.
The setup of the jobs is known.
So obviously that's the basic requirement. Setup time is independent of processing sequence. So how much time a machine will need for becoming ready, so that does not in any way has relation with processing sequence. Like as and when any job comes to any machine, the machine will have its own setup time. Setup time is deterministic. So for different situations, you can actually calculate and work out what will be the setup time. Or it can be based on the data. There will be no interruption in processing.
Due to machine breakdowns, accidents, or illness.
So while applying all these rules, we are ignoring some of such issues that might come up. Machine breakdowns, accidents, worker illness. So these are not something which are going to happen all the time. Because if the priority rules address this, then you are not able to find the optimal solution. So you can look at example 2 from your book. So different metrics can be calculated, like average flow time, average tardiness or delay, average number of jobs at the workstation or work center. So these three metrics are calculated for rules like first come, first served, and so on. Then the one gives you the lowest value. Like for example, obviously, average flow time should be lower the better. Similarly, tardiness, lower the better. Average number of jobs at the work center, lower the better. So using that, you can find out which rule provides the best solution. Let's look at one problem from the book, number 6. If you look at first part, and suppose the rule we are looking at is first come, first served, then the sequence will be do A, then B, C, and D. With SPT, the sequence D, C, B, A. With EDD, you have C, B, D, A. Critical ratio, you should get A, C, D, B. So if you are doing the calculation for the performance metrics, let's say for FCFS to start with, and we are looking at job, then your job time, which is in days, then flow time, which is again in days, due date, and days tardy. So you have A, B, C, D as jobs, and the times are 14, 10, 7, 6, so that the total is 37. So float time will be 14, 24. So you are adding 14 and 10 to get 24. Then add 7. So basically you are doing cumulative calculation. So you get 31. 31 plus 6 you get 37. So the total, if you find, will be 106. So tardiness is going to be 0 because flow time is 14. So tardiness is 0. Here you have difference of 8 between 24 and 16. Then the difference is 16 and then 20. So the total is 44. So this way you can do the calculation for SPT and EDD. I will also show you some calculation for the critical ratio. So we have A, B, C, and D. So you can also refer to the solved problem in the book while doing this. I'll give a few steps to get started. So to calculate critical ratio, first we start with the due date here. So 20 minus 0. So the first time when you are doing it, make it 0, divided by 14, which is the time. So this gives you 1.43. So if you do the same calculation for the second one, you should get 1.60, and then 2.14 and 2.83. So you can see the first one is lowest. So job A obviously has the lowest critical ratio. So therefore it is scheduled first and will be completed in 14 days. So after the completion of job A, the critical ratios will be revised. So when you do it for the next one, let's say job and critical ratio. So when you are doing for the second time, obviously you don't need A there. So it will be between B, C, and D. So the remaining numbers are 10, 7, 6, and there's no change in due dates. Earlier we used 0, but now we do 14 because for job A, when job A was completed, we have completed 14 days. So 16 minus 14 divided by 10. So that gives you 0.2. And then you have 0.14 and 0.50. So obviously this is the lowest. In the next table, you will not have any entries for A and C. And then when you are calculating the critical ratio, so from the due date, now you will be subtracting 14 plus 7, which is 21. So you'll be subtracting 21 for your critical ratio calculations. Now coming to two work center sequencing. So there are situations where you have two work centers, and the jobs when they arrive, they have to go through both of them. But how the sequencing should be done, there are certain rules. Like one of the popular rules is Johnson's rule. So this is a technique for minimizing completion time for a group of jobs to be processed on two machines or at two work centers. So the idea is that it minimizes total idle time, but several conditions must be satisfied. So let's look at the conditions. Job time must be known and constant. So actually this is a reasonable assumption, because although time required to complete a job, there could be some variability, but we are assuming that variability is very small, almost constant. So job time must be independent of the sequence. Jobs must follow the same two-step sequence. So they have to go through, let's say, work center 1 first and then work center 2 next. So it cannot be the other way. It has to be the same two-step sequence. Job priorities cannot be used. So the ones we used and solved a problem, so those priorities here cannot be applied. It's not first come, first served or due date. That's not possible. All units must be completed at the first workstation before moving to the second. So that's the condition to use Johnson's rules. So how this is done, we'll list the jobs and their timings at each work center. I'll show you an example. Then select the job with the shortest time, eliminate the job from further consideration, and then repeat 2 and 3. So this is a very simple process of assigning jobs to the work centers. So let's look at example number 4. So this is the information given. We have job that needs to be done, and then we have work center 1 and work center 2, and these are your timings, processing time, how much time each job is going to take. So A and B, A is 5 hours on each work center, but B requires 4 and 3. Then you have CD with 8 to 9, 7. And then we have EF. So what we do is, because there are 6 different jobs, we create a blank sequence. 1, 2, 3, 4, 5, and 6. So once we have that, then select the shortest one. So you can see 2 is the lowest number, and that is for job D. So that is job D. We place job D here because it is on work center 1. We start with left side. The next lowest you can see is 3, but that is at work center 2. So because it is at work center 2, we will place the corresponding job, which is B, towards the end. Then we go to the next one. Now the next one is 5, but there is a tie. So you can see 5 is at both work center 1 and 2. So when there is a tie, you can choose any work center. So let's say we choose work center 2, then we assign A towards the end. In fact, before 5 you have 4, but that B is already assigned, so we have to move on with that. Because B is already assigned, that's why we didn't look at 4. So now A is done, so we ignore A from further consideration. So A, B, and D are out, and we look at the remaining ones and the lowest number. So that number is 6, and it belongs to work center 1. So work center will put on the left side. So E goes to the left. So now E is also out of the reckoning. Then the lowest number is 8, and C goes to third position. And then obviously you are left with F. So this is how Johnson's rule is used. Now when it is applied, we make a Gantt chart, and using the Gantt chart for both work center 1 and 2, you can see we can make the assignment. So suppose this is the starting time, and this is work center 1 and this is work center 2. So suppose 0 is the starting time. So D needs 2 hours. We have E, which needs 6 more hours. So total will be 8. By 8 hours, these two jobs will be completed. Then we have C, which needs 8 hours. So 8 plus 8 is 16. And then you have F, which makes it 20. A, that makes it 33. And then we have B, which makes it 37. Now, D can be assigned to work center 2 only when it is done with work center 1. So once it is done, then it needs 7 hours. So it will go up to 9 hours. So it will take totally 9 hours before D can be completed at work center 2. Then you have 17 for E, and then you have 26 for C, and then there's the idle time here at 28, and then you have F, which gets done at 43, and then A and B. So 48 and 51. So basically, overall, it will need 51 hours to get all these jobs through work centers 1 and 2. And you have seen like how Johnson's rule can be applied for making these assignments. So scheduling actually is a very important process in any industry, and it's also very challenging. It is challenging because there is a lot of variability. Like we had a lot of assumptions when we talked about the rules and the methods, but the reality is that variability always exists. You do not have situation where your setup time is constant or processing time is constant all the time. So there are going to be variabilities in these. There could be interruptions or changes in the set of jobs. So there is no method actually which can take into account all the variables and give you the best method. Scheduling is not an exact science. That makes it more challenging. So it is an ongoing task. People who do this is their daily job. So for minimizing such difficulties, some guidelines are given here. Set realistic due dates. So don't go by like what can be done theoretically, but look at what can be done practically, realistically. Focus on bottleneck operations. So bottleneck operations are the key actually, because they are the ones which ultimately contribute to any delay or on-time delivery. Consider lot splitting of large jobs because that will make things more flexible. When you split them, then you can manage them easily, relatively easily. Theory of constraints, which were developed by Goldratt, and there is a book by Goldratt. It's called The Goal. If you go through the book, it is actually a storybook. So it's a very interesting storybook where there are characters and how they deal with a situation in their company, how they turn around, how they manage the constraints. So all the theory has been very well laid out in a very interesting manner. So I will recommend any of you who are interested, you can read the book over the summer. You'll find it very interesting. The theory of constraints goal is to maximize flow through entire system. So that's the focus of all these things we are studying in this chapter. Scheduling, the whole thing is how to make things more smooth so that the jobs can flow from one place to other place, one work center to other seamlessly. Emphasizes balancing flow. So when the demand and capacity are matched, obviously that is theoretical thing. In reality, it cannot be done. So if we go close to that and things are balanced, then it makes things easier. And everything boils down to actually improving the performance of the bottleneck. So bottleneck is that activity or process which slows down the whole system. So if it can be improved, the whole system improves. You can say it is the weakest link in the chain. So to improve performance of bottleneck, determine what is constraining the operation, why it is late, things are getting delayed, or why there is an inventory buildup, why it is taking so much of time at that particular process. Exploit the constraint. So exploiting the constraint means make sure that it is used to the maximum. So sometimes for bottleneck operations, people run those processes or machines even during lunch breaks and other times when the other machines are stopped. Subordinate everything to the constraint. So make all your plans around that particular bottleneck so that you get the best out of the constraint. Determine how to overcome the constraint if possible. Repeat the process for the next constraint. So once you improve a process to a situation where it is no more a bottleneck, but what will happen is that the bottleneck will shift to some other area. So you cannot totally eliminate a bottleneck. You may improve one process, but then the other process might become a bottleneck. Then focus and repeat the steps at that bottleneck. As an example, suppose you have operation 1, 2, and 3. And suppose operation 1 makes 100 items per hour, whereas operation 2 makes 20 items per hour, and here it is 50 items per hour. So obviously, operation 2 is the slowest, and it is a bottleneck. Now suppose the improvements lead to, from 20, it goes to, let's say, 150 due to some breakthrough improvements. Suppose you improve to such an extent that there's a huge improvement. So when it becomes 150, obviously it is no more a bottleneck. But then you have now a new bottleneck, which is operation 3. So there are different metrics people use in theory of constraint. Throughput is defined as the rate at which the system generates money through the sales. So actually, when I read the book first time, I found this definition of a throughput very interesting because they are basically talking about throughput in terms of dollars. So the rate at which system generates money through the sales. So this is a very, very interesting definition provided by Goldratt. Physical assets, the total system investment. It could be inventory, buildings and land, plant and equipment. And the operating expenses, the money the system spends to convert the inventory into throughput. So that's how Goldratt defines operating expense. So very unique and new way of defining some of those terms. Now, when you talk about scheduling services, obviously services are different, a lot different from regular manufacturing. So how you address some of the scheduling things will be slightly different. So scheduling services different from manufacturing, we all know that. Inability to store or inventory services. So that's what makes it challenging. Random nature of customer requests for service. And there's the point of customer contact. You have back office operations, front office operations. So depending on the situation, you may have more or less of customer contact. And priority rules obviously can be used in these situations. Appointment systems is very common, especially like when you take an appointment with doctors, that's the system used. So controls customer arrivals for service. And reservation system again, similar to appointment system. In fact, these two, the first two, we are talking about demand management. So reservation system, like for hotels, airlines, scheduling the workforce, that's an example of you can say capacity management. So manages capacity for service. So when you increase or decrease workforce depending on the demand, then basically you are altering the capacity. Scheduling multiple resources coordinates use of more than one resource. So those are some of the scheduling ways in services. Now, yield management is application of pricing strategies to allocate capacity among various categories of demand. So this is like people give discounts at different timings, whether it is airlines giving discount during off season, or like movie theaters giving discount for matinee shows. So they are trying to alter prices to fulfill demand or shift demand to other timings. So the goal is to maximize the revenue generated by fixed capacity. So the reason is that like if during the slack period or off season, if the seats are empty for any airline, then you cannot store them and use them in some other period. So they go waste. So why not give discount to customers who are ready to pay, and that way you can maximize the revenue. So there are fixed capacity, obviously, when we talk about hotels, motel rooms, or airline seats. And as I said, unsold rooms or seats cannot be carried over. So somehow, if they can give discount and use them, that's the best alternative. Now, there are many situations for services where scheduling requirements are similar. So hospitals, police, fire departments, restaurants, and supermarkets. So what they do is they do rotating schedules. So they set a schedule horizon, identify the work pattern, develop basic employee schedule, and assign employees to the schedule. So it is of cyclical or repetitive nature, and it can be done very easily. So service operation problems, as we have seen earlier, you cannot store them, or inventory services. Customer service requests are random, and scheduling services involves customers, workforce, equipment, all those things we have discussed.